Probability and counting rules. Here we're going to dive right into our student notes. Now that we have learned the fundamental counting rule, the permutation rule, and the combination rule, it is possible to compute the probability of outcomes of many experiments. Suppose a manager supervises 16 women and 12 men. Each shift needs 8 people. Let's go ahead and find the following probabilities. Let's find the probability that exactly 3 women are selected to work the shift. Then let's find the probability that no women are selected to work the shift. Then let's find the probability that all of the people selected to work the shift are women. And finally, let's find the probability that at least one woman is selected to work the shift. But before we begin the solution, we must first ask ourselves, does order matter? Here, since we are selecting a group to work a shift, order does not matter. We will use combinations to count the number of ways people can be selected. Remember, if order does matter, we use permutations. However, if repetitions can occur, use the fundamental counting rule. First, let's find the probability that exactly 3 women are selected to work the shift. First, we must find out how many ways can 3 of the 16 women be selected. We go ahead and use 16C3. Refer back to a previous section and go ahead and compute. Pause the video and confirm that 16C3 is 560. Now, let's go ahead and find how many ways can the remaining 5 out of 12 men be selected. Remember, the manager needs 8 people to work a shift. In this case, 3 women, 5 men. Once again, we compute 12C5, and I invite you to pause the video here and confirm that this is true. That is 792 ways. And then finally, how many ways can 8 people, either men or women, be selected from the total of 28 employees? That would be 28C8, which is 3,108,105. Now, since we are finding the probability, we go ahead and continue. So the number of ways that 3 women and 5 men can be selected is simply by multiplying 560 times 792, giving us 443,520. And since we know how many ways we can choose 8 people out of 28, the probability that we have selected 3 women and 5 men is 443,520 divided by 3,108,105, giving us 0.1427. Now let's find the probability that no women are selected to work the shift. In this case, all 8 people selected are from the 12 men. So how many ways can we choose 8 men from 12? Here it will be 495. Now we can actually go right into the probability, and here we take the 495 divided by the 3,108,105 figure we saw from the previous part A. So clearly the probability is quite low that no women will be selected. Now let's find the probability that all of the people selected to work the shift are women. First, we find out how many ways we can choose 8 people from 16 women. 16C8 gives us 12,870. Now we simply divide that number by the 3 million figure we found in part A. And again, quite a low probability. Find the probability that at least one woman is selected to work the shift. Now the phrase, at least one, is a very significant phrase. We've seen it before. And it causes us to use the following formula. 1 minus the probability that no women are chosen. And we go ahead and subtract 1 minus the probability we found from part B. So as you can see, the probability that at least one woman is selected for a committee of 8 is quite high. There are 5 houses on a cul-de-sac in a deed-restricted neighborhood. It is time for all of the houses to be painted. The Homeowners Association has approved 3 colors of paint: beige, blue, and yellow. How many different color sequences might be chosen to paint the houses? Well, in this case, since any house can be painted any of these 3 colors, we simply take 3 to the 5th power, since there are 3 colors and 5 houses. Therefore, there are 243 different color sequences. What is the probability that all 5 houses would randomly select the same color? Well, there are 3 choices for the color of the first house, but then after that, there's only 1 choice for each of the rest of the houses. So the probability really depends on just the first house. So the probability that all 5 would be randomly selected as the same color is simply 3 out of 243. A decorator is selecting colors for the den walls, the sofa, and the accent chair. She can choose from 10 colors for the walls, 5 colors for the sofa, and 3 colors for the accent chair. In how many ways can she choose the colors? Simply put, 10 colors for the walls, 5 colors for the sofa, 3 colors for the accent chair. Multiplying gives us 150 ways that she can choose colors. What is the probability that if colors are randomly selected, she chooses seafoam green walls, yellow sofa, and turquoise accent chair? The probability of this occurring is really just 1 out of 150, because once again, she is choosing one specific color sequence out of a possible 150. In a company with 9 executives, of which are 4 women and 5 men, 3 are selected to attend a management seminar. Let's first start by finding the probability that all 3 selected will be women. First, in order to do this, we must count how many ways we can actually choose the women. Here, there are 4 women, and we will be choosing 3 of them. So 4 choose 3 gives us 4 ways that 3 women can be chosen. And there are 9 executives, and 3 will be chosen to go to the seminar. So 9C3 equals 84 are the number of ways that 3 people can be chosen from a group of 9 executives. Now all we simply do is we take the number of ways that 3 women can be chosen and divide it by the number of ways any committee of 3 will be chosen from the group of 9, reduce, and here we get 0.0476. Now also, the above probability also happens to be the same as the probability that none are men. Now, the next one, let's go ahead and take the same problem and now find the probability that all 3 selected will be men. So once again, we choose out of 5 men a group of 3, and there are 10 ways to do so. Once again, in how many ways can we choose 3 people out of 9? That would be 84. And simply dividing 10 divided by 84 gives us 0.1190. Now let's go ahead and find the probability that at least one of the people selected will be a man. Once again, there's that phrase, at least one. We need the same formula of 1 minus the probability that none are men. Now, as you saw from part A, we already calculated the probability that none are men. So we go ahead and use that numerical value. 1 minus 0.0476 is 0.9524. So a pretty high chance that the committee of 3 will at least have 1 man. Part D, let's find the probability that 2 men and 1 woman will be selected. Let's keep in mind, out of 4 women, the number of ways that you can choose 1 woman is simply 4. Out of 5 men, the number of ways you can choose 2 of them will be 10. Now this one's a little bit different. Here, what you'll do is you'll multiply the 4 times this 10, then divide it by the 84. And now reducing, we get 10 out of 21, which is 0.4762. And remember, many times the word "and" is associated with multiplication. Let's do another one. Let's now find the probability that 2 women and 1 man will be selected. First again, we must find the number of ways that out of 4 women, 2 will be chosen. Here that will be 6. And again, plug those numbers into the formula and confirm. And then finally, the number of ways out of 5 men can 1 be chosen is simply 5. And I invite you to pause the video here and try to find this probability. It's very similar to the last part D. Here we have 6 times 5 divided by 84, which reduces to 0.3571. In a lottery game, one selects a 3-digit number with repetition of digits permitted. Let's find the following probabilities. First, let's find the probability that all of the digits are the same when the winning number is selected. Now here, there are 10 ways to select the same number for all 3 digits. Therefore, there are 10 to the 3rd power, which is 1,000, ways to select the 3 digits. Therefore, the probability that the winning digits are all the same will be 10 out of 1,000, or 0.01. Let's also find the probability that a person's favorite 3-digit number is selected. The probability that a person's favorite 3-digit number is selected will be 1 out of 1,000. And the reason why is the lowest number is 000 up to 999. These are the only 3-digit numbers permitted. There are 1,000 of these, and the 1 favorite number is selected. Again, 1 out of 1,000. Next, the gift basket department at a local upscale grocery store has pre-made gift baskets containing the following combinations in stock. Let's find the probability if 1 basket is chosen at random that it contains coffee or candy. Keep in mind that some of the baskets contain both coffee and candy. Now there are 77 baskets that are offered total. 43 contain coffee, 22 contain candy, 10 contain both. So the probability that the basket contains coffee or candy is the probability of the baskets that contain coffee plus the probability of the baskets that contain candy. And then so we don't double count, we subtract the probability of baskets containing both candy and coffee. 43 plus 22 minus 10 is 55, and we get 55 over 77. .7143. Let's now find the probability that if one basket is chosen at random, it contains tea, given that it contains mugs. This is an example of conditional probability. There are 23 mugs. Of these mugs, 10 contain tea. So the probability that the basket contains tea, given that it contains mugs, will be 10 out of 23, which is 0.4348. If one basket is chosen at random, find the probability that it contains both tea and cookies. Well, there are 12 baskets that contain both tea and cookies. And since there are 77 baskets total, we get 12 out of 77, or 0.1558. Find the probability that if 3 baskets are chosen at random and not replaced, find the probability that all 3 baskets contain mugs. Now this will be a situation where we multiply. Now since there are 23 baskets that contain mugs in this column here, the first basket will be 23 out of the full the first basket will be 23 out of the full 77. And since they are not replaced, we now have 22 baskets out of 76, and then we finally multiply by 21 baskets out of 75, giving us an estimate of 0.0242. Now let's find out if 3 baskets are chosen at random, find the probability that none contain mugs and there was no replacement. Again, we're going to be multiplying. The baskets that do not contain mugs will be this 20 plus 12 and this 10 plus 12. Adding all those up, we get 54. Therefore, if I choose one basket at random, the chances that it does not contain mugs will be 54 out of 77. Then choosing the second basket will be 53 out of 76. Then 52 out of 75. Multiplying, we get 0.3391. Now, what's the probability if 3 baskets are chosen at random and not replaced that at least one contains a mug? There's that phrase again, at least one. So remember, whenever you are using the phrase at least one, it's the same as saying 1 minus that they have no mugs. So we simply take the answer from the previous part and subtract it from 1. Here we get 0.6609.